Okay, this is not a new lesson so much it is a continuation of a previous lesson. This is actually the second part of a set of examples we were looking at optimizing distance. Now the first one ended up being 20 minutes long, and so I think I made a good decision in splitting it. And we may not even do the other two examples here. We may only do one, and then I may just sketch out the framework of the other one, just because, again, they are quite involved. So I'd rather do a good job of explaining this next one than worry about trying to get through them, because in the end they actually are all quite similar as well. Even though they're all involved, they're also quite similar. So let's start off with the question itself. We've got Ian's house is located 20 kilometers north of Nada's house. One morning, Ian leaves his house and jogs due south at 8 kilometers per hour. At the same time, Nada leaves her house and jogs east at 6 kilometers per hour. They both run for 2.5 hours. So when are they going to be closest to each other? So first of all, we need to visualize this situation, and that would help if I could drag this over. One more try. Okay, so Ian starts here 20 kilometers to the north, so 20 kilometers. And he said he heads south at 8 kilometers per hour. So that is going that way. Nada, on the other hand, is going to go this way at 6 kilometers per hour. So the question is, for example, right now, if we just started with the distance between them, we would draw that line and we would use the Pythagorean theorem to come up with, I'm sorry, that's not correct. Get rid of that line. Right now, if we were to draw the distance between them, it would be here. It would be 20 kilometers. As they move, so for example, Ian's part moves down, but at the same time, Nada's part moves to the right, and so that's going to be a different distance. And then Nada will continue to move to the right, and Ian will continue to move down. And so the amount of distance between the two of them is going to vary over time. And just as I did in the previous question, I put together a little GeoGebra demonstration of this. So here we have Ian up here at the top, and we have Nada down here at the bottom, and the current distance between Ian and Nada is equal to 20. Now I'm going to grab a hold of this slider which represents time. So it starts off with t equals 0, and as time progresses, you can see Ian is moving south. And so for example, let's put t at 1. So Ian's moving at 8 kilometers per hour. So Ian went from 20 to 12, covering a distance of 8 kilometers. Nada is traveling at 6 kilometers per hour. So in 1 hour, she would have ran 6 hours. And the distance between the two, Ian's remaining distance from the origin is 12. Nada's new distance from the origin is 6, and if we apply the Pythagorean theorem to that, we end up with approximately 13.42. Now, up here, I've also included a y value for that. That actually represents that. So you can see that y value is at around 13.42, and it's just tracing where they are. So for example, when t is equal to 0, that y value for the distance is equal to 20. When t is all the way over here at 2.5, that y value turns out that is 15. So they're 15 kilometers apart. And I can actually do something quite interesting here with GeoGebra, which is I can go into this object's properties and say I want to see the trace of it. And now I can actually show what that distance is as we kind of scan through time here. And you can see there's a distinctive minimum here. So there's a minimum around here, and I'm not going to go to that value, but you can see that it occurs here. You could work backwards. It occurs when Nada is at around 9.5 kilometers, so you'd be able to work backwards and do the calculation. But we're going to use calculus to come up with that value. We'll come back to this once we're done that. So what we're looking at is, I'm just going to get rid of that little piece of clutter. So what we are looking at is, once again, the distance formula. So the distance formula is that x2 minus x1 all squared plus y2 minus y1 all squared, and then that whole thing square rooted. So the distance from Ian to Nada is going to be xn minus xi all squared plus yn minus yi all squared, all square rooted. It doesn't matter which one you put as the second point and which one is the first point. I think of Ian as running towards Nada's direction, so that's why I made Nada kind of the destination. But it actually doesn't matter, because whatever this difference is, we're squaring it. So what do we know about these values? What is Nada's x-coordinate? Well, Nada's x-coordinate is based on how far she's traveled, because she's changing in the x direction. So at any point, her x-coordinate is 6t, but her y-coordinate stays 0. Ian, on the other hand, he's actually going to stay on the y-axis, so his x-coordinate is always 0. His y value starts at 20, and then from there we're going to be subtracting 8t as he moves along this path heading south. And so putting all of that together, x-coordinate of Nada is 6t minus the x-coordinate of Ian, but that's just equal to 0. So this is going to be 6t minus 0, or 6t all squared. You know what? Let's not cut corners. We can afford to write this out. 6t minus 0 all squared plus the y-coordinate of Nada, which is equal to 0, minus the y-coordinate of Ian, which I'm going to put in a bracket here, 20 minus 8t all squared, and then that whole thing is square rooted. And now we can simplify 6t all squared plus, now this is 0 minus this thing, but minus this thing is just reversing the order. 20 minus 8t becomes 8t minus 20 all squared, square rooted. Some simplifying, 36t squared plus, and now this one I'm going to expand, that becomes 64t squared minus 320t plus 400, and that whole thing is square rooted. 100t squared, I add the quadratic terms, minus 320t plus 400. I could go ahead and start doing the calculus now as far as taking the derivative, but I do notice these numbers are kind of large and unwieldy. And so what about common factors? I can see 10 goes into all of these. I also see 2 goes into all of these. So actually 4, yeah, so 20. I can take 20 out of all of these, and I end up with 5t squared minus, when I take 20 out of this one, I get 16t. And when I take 20 out of that, I get plus 20. And don't forget that whole thing is still square rooted. And now we are actually ready to take d prime of t. No, that's not what I wanted. I wanted an eraser. D prime of t is equal to, so I didn't change this to exponent notation, but hopefully we're familiar enough with that it's to the exponent 1/2. So it becomes 1/2 square root of 20. That part doesn't change. And then, so what I'm essentially doing is I'm taking that constant out right away, and now I'm going to take 5t squared minus 16t plus 20. That's now going to be the negative 1/2. And then I take the derivative of what's inside the bracket, which is going to be 10t minus 16. So I'm going to put in that extra line. What I ended up doing was I ended up taking out square root of 20 and leaving that as a constant in front, and then 5t squared minus 16t plus 20 to the 1/2, and that's the part I took the derivative on. Okay, so let's see, what do we have here? In the numerator we have square root of 20, and I have 10t minus 16, which actually has a 2 that can factor out of that, leaving me 5t minus 8 over 2 times 5t squared minus 16t plus 20. And that's to the 1/2, and it's the positive 1/2 because we've moved it to the denominator. 2's divide out. And you might wonder, why am I worrying about factoring these things? I've mentioned this before. I've mentioned it in class as I've been working with people individually, which is, in general, when we solve these things, we are going to be looking to, and I'm going to write that first, we're generally going to set the derivative equal to 0 because we are looking for the extreme values. And that occurs when the slope of the tangent is equal to 0, which means the first derivative is equal to 0. So now I get 0 equals, but no denominator can cause this to be equal to 0. So instead we look at the numerator. And so we end up with root 20 times 5t minus 8. And obviously root 20 is just a number, so I actually end up with 5t minus 8 equals 0, or t is equal to 8 over 5. T is equal to 1.6. So this is possibly an absolute or possibly just a local extreme value. So we do still have to test our endpoints in particular. And we have to test this point as well. So what we need to do is figure out, what is d of 0? Well, we already know d of 0. That's equal to 20. That was when this whole thing got started. What is d of 2.5? You might remember that from when I showed you the GeoGebra slide. That was actually equal to 15. But I think I will use this simplified expression. So it's going to be, let's see if I can fit it. I can. Square root of 20 multiplied by the square root of 5 times, and instead of 2.5, I'm going to write this as 5 over 2 all squared, minus 16 times 5 over 2 plus 20. Just want to go back. Is there a simpler form for this that we could have used? Not in particular. I mean, I could have made it a bit easier, maybe. So from there, I end up with square root of 20. I'll be interested to see how and why this is going to turn out to be 15. So this one ends up being 5 over 2 all squared, which is equal to 25 over 4. And then 5 times that 25 is equal to 125 over 4. And then we've got 16 over 2, which is just 8. So negative 8 times 5 is minus 40 plus 20. And that's all going to be square rooted. So we end up with the square root of 20. And now we have negative 40 plus 20 is minus 20. And so obviously it's not going to work out. Maybe I was wrong. Maybe it's not exactly 15, because this works out to be 125 divided by 4 is, I'll leave that as a fraction, and then this is going to be minus 20, which is minus 80 over 4, which is equal to square root of 20 times the square root of, and that's going to be 45 over 4, which is the same as the square root of 20 times the square root of 45 over 2. And I think we can stop kind of dancing around this for now. Let's just find out what this value is equal to. So we've got the root of 20 times the root of 45 divided by 2. And that's equal to, well, look at that. It actually works out to be equal to 15. So I can see it now. quite silly of me that I didn't see it before. We've got 45, which is 9 times 5, or in other words, a square root. And then over here, we've got 20, which is 4 times 5. So square root of 9 is equal to 3, square root of 4 is equal to 2, and then we've got root 5 times root 5, which is just equal to 5. So of course this works out to be a whole number, and that is equal to 15. Kind of embarrassed that I resorted to the calculator on that one. Okay, so we've got a value of 20, we've got a value of 15, so now what we have to do is find out whether or not this is a minimum. Could be that this one's a minimum. 20 obviously isn't the minimum, but this one could be the minimum. So now I also have to try d of 1.6. And d of 1.6, I think I'm better off in this case actually just figuring it out using the 1.6. So that ends up being square root of 20 times the square root of 5 times 1.6 all squared minus 16 times 1.6 plus 20. And I end up with, and I'm just going to go straight to the calculator on this one. So 5 times 1.6 squared minus 16 times 1.6 plus 20 equals, we're going to take the square root, and actually, well, we're going to multiply that by 20. And, oh, look at that. It turns out to be actually a perfect square. This ends up being the square root of 144, which of course is just equal to 12. And so that tells us that this is our absolute minimum at t equals 1.6. And if we go back to here, well, that's what we were looking at, and I didn't show you this, but if we go back to that point where it was at a minimum, you can see there occurs when t is equal to 1.6. So let's make sure we're answering the question. The question says, if they both run together, sorry, they both run for 2.5 hours, when will they be the closest together? And so we actually do have our answer to that. Therefore, they will be closest after 1.6 hours. If you want to be really fancy, you could change that into minutes or even seconds if you wanted. Okay, so again, this has already gone on for longer than I would have hoped, but to do a thorough job and to explain it, that's just going to be necessary. So as you're going to see, for this one, I'm just going to set up this question. You're going to see that this is more of the same. We're using the distance formula because that's what we're doing. We're optimizing distance here. A train leaves the station at 10 a.m., travels due south at 60 kilometers per hour. That's very familiar. It's very similar to the question with Ian and Nada. Another train has been heading due west at 45 kilometers per hour and reaches the same station 1 hour later at 11 a.m. So in other words, this other train is an hour out. At what time of day are the two trains closest to each other? So this is really identical to what we were talking about in the previous question. It's just the difference here is instead of starting, well, if you turned this on its side, actually, it would look like this was Ian heading south and this was Nada moving away. So it's just a different perspective thing. You have to figure out, you have to assign coordinates. What is the starting point for this one? The hard part is the fact that you've got this time discrepancy. So you have to use the speed of one of the trains to figure things out. So for example, this train is moving at 45 kilometers per hour. So if it's going to reach that station in 1 hour, then how far away must it be? Well, it has to be 45 kilometers away if it's going to get there in an hour. Now, I've given you numbers here that work just by common sense. You might have to do a little bit more work on this if it was more complicated than this. So that means that this distance is decreasing. It starts at 45 and then it's going to decrease until it reaches 0 when the train pulls in. This train starts off at the station, so its distance from the station is 0, and it moves away at 60 kilometers per hour, which means its distance is just 60 multiplied by the amount of time that has passed. And just like before, right now they're 45 kilometers apart. Eventually, the trains might be there, and then that will be their new distance, and then the trains will be there, and that will be the new distance. And we are trying to find out, when is this line a minimum? So we're once again going to make use of our distance formula. And in this case, we end up with the x-coordinate of this first train, which is 45 minus 45t. The x-coordinate of the second train is 0, so that's all squared, plus the y-coordinate of this first train, which is 0, minus the y-coordinate of this other train, which is actually going to be negative 60t, all squared, and then square rooted. Notice I switched the order. This time I did the first minus the second, the first minus the second. It doesn't actually matter because of these squarings that are going to take place. And then we expand this, and you can see we end up with a problem that looks very similar to the one that we just finished, and actually very similar to exercise number 1 as well. This is worked out in your textbook, so if you have access to that, you can also check it. I also don't have a fancy GeoGebra slide for this one, so it almost doesn't seem worthwhile to do it. I will leave that one for you to try on your own, and then of course if you have any questions you can just let me know. So just to recap, I'll go all the way back to the beginning, and there is the other work that you are going to be working on yourself, and bringing your questions to me if you have any.